Need to stop. No, okay, now I see it. Okay.
Okay, good morning, everyone. Welcome to a new seminar by IAEA. We are very glad today, very welcoming Dr. Matilde Bicocci to the IAEA. Is it your first time at the IAEA, probably? Or
Yes,
second?
it's the first time here.
Okay. We are, it's a honor for us to have Matilde with us here for the seminar. Matilde Bicocci presented her PhD in Bologna in 2020. She's a very well-known expert, international expert in the ISM in galaxies, either star-forming galaxies, but also in the end. And in general, I would say that's a very well-known expert on the transfer problems and ionization problems in galaxies. Matilde, as I said, presented her PhD in Bologna in 2020. Then we went to with a postdoc position in Padua. Then she was working on galaxies in clusters, but also, well, the jellyfish galaxies and the interaction with the intergalactic medium and so on. Then she moved to Space Telescope Science Institute with a postdoc position. Stayed there for some years, and she has been doing a lot of work there, also supporting, but also on her career. And later he got a position, a staff position at ESA, or astronomer, also at Space Telescope, but in relation with James Webb and also STIS and other instruments. Very, very interesting science. We are, waiting, eager to see your results on the infrared to UV view of the nearby. It's like a high-set analog for James Webb. I mean, I would say local analog for ionization gas.
Yes.
Thank you.
Thank you very much, Pepe, and thank you very much for having me here and giving this talk overview of the works I've been doing in the last few years. As Pepe said, I am ESA or astronomer at Space Telescope, which means that basically 50% of my time I work for STIS, the instrument STIS on Hubble Space Telescope. So I do user support and support to the community and support to the instrument itself. And the other 50% I do science. And the work I'm presenting today, I've been doing this work in collaboration with many people. Some of them are listed here. There are many more. And in particular, I want to highlight the contribution of two early career researchers, two postdocs at the Space Telescope, Macarena Garcia del Valle and Ryan Rickards-Vogt, because they contributed a lot to the work I will describe later in my slides. So I want to start with this beautiful overview, this beautiful timeline of the history of our universe, where you can see highlighted the main epochs of the history of our universe. And in particular, now that we are in the James Webb era, we know we are starting to reveal many more things about the epoch of reionization. That is when the first galaxies, they started to reionize the universe, because ionizing photons emitted from sources within these galaxies, within these first systems, they escaped and they started to reionize the universe. There are still many unknown questions about these. There are a couple of reviews that I highlighted there on the top that really give an overview of what we have learned so far with James Webb. I just want to highlight a couple of few recent results. For example, with James Webb, now for the first time, we can see very high redshift systems. This is, I think, so far the farthest galaxy ever observed, spectroscopically confirmed. That is an object at redshift 14.44. And you can see over here some far UV emission lines that characterize this galaxy and that reveal its redshift. And here instead you can see a closer galaxy, that is at redshift 10.6, the famous GNZ11. Here you can see much better the far UV emission lines, and also some optical emission lines start to pop up over here. And for these systems, it's amazing the amount of information that we are discovering thanks to James Webb. I want to highlight a couple of results here. This is the the new version of the mass metallicity relation from Curti 2024. It is known that galaxies, like that the stellar mass and the gas phase metallicity in galaxy are related. And in black over here, it is shown the local relation that is found that as a scatter, of course, but it's kind of defined over here. And this work of Curry 2024 added to this an amount of galaxies, like 150 galaxies between redshift 3 and 10. And you can see where these galaxies are located. They tend to have generally a low metallicity, not too low. The median is like a 20% solar, and of course lower stellar masses than the majority of the nearby galaxies. But they show a lot of scatter, and this scatter is still under investigation. There are still many things that we need to understand about the physical processes that are contributing to this scatter. And in terms of element abundances, it's not only oxygen that people have started to look for. There have been many new results that show this puzzling nitrogen enrichment, so the enrichment of nitrogen with respect to oxygen, because in theory, like there is a local relation that is found for H2 regions that is shown over here, and there are some systems in the redshift universe, including GNZ11, the galaxy I was showing before, and another few systems that instead show a much higher nitrogen with respect to the oxygen. So they are outliers. Also, this is still under investigation. There are different theories that people are testing, and it can also be like one of the reasons can be the conditions of the star formation at high redshift, the fact that star formation is very bursty. It can happen in very dense environments. And in some cases, for example, in the case of GNZ11, there could even be an AGN, and this, of course, means that it's important to take that into account when you measure the nitrogen abundance. And in general, measuring the nitrogen abundance in the correct way, and in general, measuring all these quantities in the correct way is one of the things that we need to take care when we analyze these high redshift systems. Since, GNZ11, as I was saying, it could be an AGN. There are actually other works that instead have propose a different theory. But in general, the topic of the ionizing source at high redshift is a very hot topic. There are still many things here also that are not completely understood. For sure, what we know is that the classical diagnostic diagrams that are typically used to separate star formation AGN, they are not so useful at high redshift. This is, for example, the typical, like the very well-known N2BPT diagram. And the points here, the yellow points that you can see here, are AGN at around redshift 4-7 that are revealed by JWST and are defined as AGN because they show broad permitted lines, like broad H alpha or broad H beta, and not a broad component in the forbidden lines. And of course, they would be classified as star-forming galaxies according to classical diagnostics. The failure of these classical diagnostic diagrams was known. Like, it's known that there is a degeneracy between the ionizing spectral shape, the gas phase metallicity, and the ionization parameter, but now it's even more evident. Now that we have all this system at high redshift, we see this much more clear than before. And there have been attempts to propose different diagnostic diagrams that use other optical or even UV emission lines to separate between star formation, AGN, etc. There are many degeneracies also here. Like, this is one example from Mazzari 2024, but there are many works that have been looking into new diagnostic diagrams. And of course, another way that people are using to classify AGN at high redshift is the use of broad lines, like, as I was saying, the broad permitted H alpha, broad H beta, that now people find in many JWST spectra at high redshift. And from there is another puzzling results that is still under investigation. That is the fact that when you measure the black hole mass of these high redshift systems, it seems overmassive with respect to local relations. This seems intrinsic because it has been found by different studies, and so it doesn't seem a problem in the measurements, and may have consequences on the feedback processes in case it is true. Of course, this is all under investigation. So I wanted to highlight here some of these high redshift results to show how many puzzling discoveries we have been looking at, and to highlight that for these redshift systems, the thing is that we are limited to a small range of, with a small range of spectral information, because we are looking at the far UV for very distant systems. For a slightly closer system, we can see some of the optical emission lines, but it can become difficult to have a broad overview of what is going on. And that is why I want to highlight how important it can be to have instead local analogs, local laboratories, so selecting systems in the local universe, systems that are metal poor, have a low mass, are compact, are starburst. They are not exactly the same things that we see at high redshift, of course, but they can have very similar conditions that we can use to understand what is going on. This is, for example, a UV spectrum of one of these nearby local analogs, where you can see UV emission lines, very high ionization UV emission lines, typically observed in some of these redshift systems. And of course, for this object, we can get a much higher spectral resolution. We can get and also spatial resolution that we don't have at high redshift. This was in particular with the focus on the UV and the fact that we can measure the UV in the local universe with Hubble and in the high redshift universe with James Webb. This was one of the focus of the CLASSI survey. CLASSI is a treasury program, Cycle 27 program. The PI is Daniel Berg. And the aim of CLASSI was to put together a sample of nearby star-forming galaxies, in particular 45, but selecting them in a way to have characteristics that are more similar to the redshift universe. In particular, here on the left, you can see the star formation rate versus stellar mass. The star formation rate of the classic galaxies is shown in purple, and it's higher with respect to the local relation, and so make them more similar to redshift systems than than typical local galaxies. There have been many works published for CLASSI so far, and if you are interested, there is the CLASSI website where you can find all the information, all the spectra. But the main thing is that we have high resolution UV spectra covering from the Lyman alpha up to the carbon 3. Plus, all these systems have also optical spectroscopy from ground-based observatories. And so we can really have an overview of the properties of these systems in terms of abundances, presence of outflows, and feedback. And in particular, the work that I've been doing on the CLASSI survey was to study the interstellar medium properties using UV and optical emission lines, comparing them and see how we can calculate the interstellar medium properties in terms of gas density, main ionization source, but also metallicity, etc., using UV lines instead of optical lines. Here I want to show you a couple of results from the CLASSI work. Here on the left, you can see the gas density that I derived using different tracers. In particular, the squares over here I derived them with using sulfur 2 optical lines that are tracing the low density regions in these star forming systems, while the other points, the yellow, green, and the other points on the top, they show the densities that I calculated with the UV tracers, and so mostly carbon 3, but also silicon 3, nitrogen 4. In general, what you can see is that the densities derived in the UV with this tracer is more or less 2x higher with respect to the optical. And the main takeaway point from this is that when you measure ISM properties, it's important to take into account which regions of the gas you are tracing. And so the fact that sulfur-2 lines trace the low ionization region and that carbon-3, for example, trace the intermediate ionization region. And it's important to compare apple to apples in this sense. The plot on the right instead, it's what we think is the best UV tracer to distinguish between ionization sources, and it shows the carbon-3, helium-2 versus oxygen-3, helium-2 line ratios. You can see the overplotted the AGN models, AGN and shock grids, and the classy points that are located in a different locus with respect to the models. And so there are two classy galaxies that are located closer to the AGN and shock-dominated regions, but we believe that they were located there because they are low metallicity, like they are the most metal-poor system in classy. I will go back to these later in the talk, but in general, this is a good UV diagnostic diagram to discriminate between ionization sources. And in general, these information on the ISM plus all the other works on classy have started to be applied in high redshift works to understand what is going on. And so we hope that these works will be even more useful in the future. To go back to the previous overview, so the overview that I was doing, that I was showing you before, I was saying that local analogs are important because we can get many more information. Well, we can get more information about them than high redshift systems. And I was showing you this UV spectrum that we can get with the Hubble Space Telescope. But of course, we can get many more information for them because we can get optical spectra using ground-based observatories. We can get infrared spectroscopy from JWST, for example. We can get radio, sub-millimeter, X-ray data. We can really have a complete overview of what is going on in these systems. In particular, now it was just approved in cycle 4. It was approved the CLASSIR survey. CLASSIR is an extension of CLASSY to the mid-infrared using MIRI. The PI are Daniel Berg and Bethan James. And CLASSIR will really study, will give a complete overview from the UV to the mid-infrared of these high redshift analogs. And so stay tuned for more results in this sense. What I want to present you today is my first work on JWST MIRI data of one of these nearby analogs, that is the galaxy SBS 0335-052e. I'm calling this galaxy here the perfect local high redshift analog. Of course, I know that it doesn't exist a perfect analog, but the fact is that this galaxy is very well known. It's part of classy, but it's also very famous and has been studied by so many people in the last 20 years or so, even more. It's extremely metal poor, like it's 5% solar, as a compact, vigorous starburst with massive young clusters. You can see here in this figure, the figure shows the UV image, and the black contours are the H-alpha contours. From the UV image, you can see that there are some regions that are more concentrated, let's say, and these are the superstellar clusters that were discovered in this system from 1 to 6. And these superstellar clusters have an age that goes between 4 and 15 megayears, so very, very young star formation, all focused in a region that is around 1 kiloparsec square, more or less. It's a very compact, dense star formation, starburst. From the H-alpha, you can see there are also regions of diffuse recent star formation, like this region S7, S8, etc. There is also ULX that is discovered in this system from previous works using X-ray data. The UV spectrum and also optical spectrum of these objects show very high ionization emission lines that are typically observed in high redshift systems. It also shows neon 5 in the optical, and this was discovered actually from Tuan and Isotov in 2005 and was published again by Atano 2024. And in Atano 2024, they even proposed that this neon 5 emission could mean that there is an intermediate massive black hole. And also, cherry on top, it also shows a broad H alpha profile. And so it could really be similar to these high redshift systems that show the broad H alpha, like the broad permitted lines, but not broad forbidden lines. So all these elements make this galaxy, let's say, the perfect local high redshift analog. Oh yes, sure.
Supposed to be AGN would be in the image?
Well, this was not discussed by previous works because the work from Atano 2024 that discovered the neon, well, that talked about the neon 5, it used the long slit spectroscopy. So it's not obvious to understand where is the AGN if there is one, and I can discuss this later. But if there is an intermediate massive black hole, maybe it could be around this region over here, because we see that the neon 5 is coming from there. Spoiler, a couple of slides later. But it's interesting that instead the X-ray emission is focused, like is centered in this region over here, where there is this ULX. And for this system in cycle 2, I got the approved JWST program to observe the MIRI MRS, to observe this object with MIRI MRS. This object and actually other objects, and I will go back to that later when I show you other results for the survey. But I want to focus about this now. And this is one of the first images that we saw when we looked at the reduced MIRI data. This is a portion of the cube that basically collapsed the light between 12 and 17 micron, more or less. And what we noticed is that there is a clear point source shape over here that you can probably see. The point source seems to be located in this region over here, where there is the superstellar cluster 1. And of course, we were puzzled when we saw this because we weren't expecting it. But actually, then we realized that it's typical to see point sources when you look at this kind of system in the mid-infrared, because there are many compact star-forming regions. Even NICMOS data, HST NICMOS data of this system showed 3 point sources in the past with a similar spatial resolution than James Webb in the near infrared. So it's very typical, apparently, to see these point sources. And of course, the point here was that we wanted to study what was behind the point source. And to understand to spatially study the conditions in this galaxy. So what we did is that we modeled the point source emission, as people do usually with quasars. We modeled the point source and we subtracted it. Modeling the point source, we could extract one spectrum for the point source that is shown over here. The spectrum of the point source, it is interesting because it shows many emission lines, but not high ionization emission lines. Like there is no neon 5, or there is no neon 5, for example, coming from this region. But a peculiar feature that is visible here and not as well in other parts of the galaxy is the silicate feature that is very deep and indicates an attenuation that is around 15 magnitude. It's a very high attenuation that was already proposed in previous works in the near infrared. The difference here is that we can locate it. We can say that the very dusty region is located over here, and while the average AV in other regions is much lower than that. And this is probably also causing the point source emission in the mid-infrared. This is very bright in the mid-infrared. There is a lot of dust over there. There is a very young star-forming region that is more or less 4 mega-year or so. And there is no high ionization, like not very high ionization like neon 5. Once we remove the contribution of the point source, we can spatially resolve the emission lines in this galaxy. And the superpower of MIRI-MRS is that it covers a range of, like, it covers from 5 to 28 micron. And so you can have really a range of ionization potential. Here I'm showing maps from sulfur 4 up to neon 5, but actually there is also neon 2 and other lower ionization lines that you can trace. But you can see how the ionization potential from more or less 35 electron volt goes up to the neon 5 that has instead an ionization potential of 97 electron volt. This is the first time that the neon 5 at 14.32 at 14.32 micron is detected in a blue compact dwarf, because before there were only upper limits. It's interesting that the other transition at 23 micron more or less is not detected. This could be a matter of density or probably a matter of density. And it's interesting that the neon 5 emission is coming from this region over here, that corresponds to the older clusters, the clusters that are older, the clusters that are around 15 mega-year or so. And the peak is coming from this region here that is more diffuse in H alpha that I was showing you in the previous image. Neon 5 was detected in the optical, as I was mentioning before, but from a long slit spectroscopy. Instead, for the first time here, we can spatially resolve it and locate it in this part of the galaxy. Usually, this line is evidence of AGN activity, because it's difficult to ionize it with just star formation, but there are still many open questions about it. Well, in order to investigate more about this neon 5 emission, what we did, we looked at BPT diagrams, but in the infrared. And in particular, we looked at the ratio of the neon 5, neon 2 versus the neon 3, neon 2. You can see the plot is color-coded, the scatter plot is color-coded as a function of the oxygen for neon 3, and the image is shown here on the right, so you can have an idea more or less of where the points lie. So the strongest ratios are coming from a region that is really located around these older clusters, plus the diffuse H alpha emission. It's interesting that all the line ratios that we can measure from the neon, in terms of neon 5, neon 2, are higher with respect to the historical star formation AGN separator that was proposed by INAMI 2013. In the paper, in the published paper of this work, we explored also star forming grids, we explored X-ray binary models and shock models, but none of them could reproduce the low ionization and these high ionization lines together. So the only models that can reproduce the observed line ratios are shown here in red, and are the intermediate massive black hole models from Richardson 2022. You can see different shades of red, because this represents different range of AGN fraction, from 4% to 100%. But actually, in order to reproduce the point, you need grids that are between 4 and 16% of AGN fraction. Oops, sorry, this is wrong. Okay. I was mentioning at the beginning of my talk that we looked at the UV and we were finding the best UV diagnostic to discriminate between mechanisms, and there were 2 points that were very close to the to the division between AGN shocks and star formation. And these 2 points that are over here, one of the two, the yellow one actually, it's SBS 0335, 052. So it could be that this galaxy is really hosting an intermediate massive black hole, and that is why it is so close to the, let's say, to this boundary. And indeed, if we redo this plot and we overplot this time intermediate massive black hole models instead of AGN grids, we start to see that these intermediate massive black hole model, they go over the AGN locus and they go in the star formation region. And it's good to see that this grid over here that can reproduce SBS UV line ratios is the same that can reproduce also the mid-infrared line ratios. So the models, the same models can reproduce different line ratios in different, for the same object. We still think that this is the best UV diagnostic to discriminate between mechanisms. The thing is that there is a new caution to be taken into account because there is this degeneracy with intermediate massive black hole models that was not known before. So now we need to take that into account when we explore high redshift systems. Another thing I want to say about this work is that of course, you can say, okay, but what do we care about the mid-infrared since we cannot see these in the high redshift universe. We cannot see the mid-infrared in the high redshift universe, and this is totally true. But the neon 5 has an optical transition, and this optical transition can be seen with James Webb, with NIRSPEC, for example, and has been observed in few systems. These are some of the works where this transition has been observed. And this is one of the diagnostic diagrams that has been explored. The helium-2H beta, neon 5, neon 3. So these are all optical line ratios. Our galaxy, SBS, is not the first blue compact dwarf that shows the neon 5 in the optical. And indeed, here I overplotted other objects from the literature. And this blue point here on top that is a bit higher, like it's 1 Bex higher with respect to the others, is a redshift 6 system from discovered from CHISON 2024. And the grids over here are the Richardson intermediate massive black hole models. So definitely it's important to explore more these kind of systems, these neon 5 emitters. And we can do this with this kind of models, like intermediate massive black hole models, to better understand what is going on here, because it's still not super clear what is going on. Really last plot for SBS that I want to show before moving on is another diagnostic diagram. This is taking into account only low ionization lines. So, well, lower ionization than neon 5. So I'm taking into account sulfur 4, neon 2, neon 3, and neon 2 ratios. And the magenta line that you can see here, it's an empirical linear relation that is found in general for galaxies, including blue compact dwarf, because the line ratios on the y and x axis, they both trace the ionization parameter, and so they are related. It's interesting to see that SBS, these are all the points that are measured for SBS. These are specially resolved, line ratios. They all lie a little bit below what is generally found for other galaxies, and they cannot be reproduced by again star forming models, X-ray binaries, and shock models. So even the lower ionization mid-infrared lines cannot be reproduced by models that are not intermediate massive black holes. And the intermediate massive black hole models instead are shown here, again from the colored as a function as the AGN fraction. So this is interesting, and it is telling us that probably there is a limitation in current photoionization and shock models at low metallicity that we still need to understand, because many blue compact dwarf have similar line ratios than SBS, They are located more or less over here as SBS. And so either all of them have entering a massive black hole, or we need to understand what is going on. And this is all open work, I think. Since I was mentioning about other blue compact dwarf, of course, I need to talk also about another very important high-redshift analog, the case of 1SVK18. 1SVK18 is also, a well-known system. It has even a lower metallicity than SBS, because SBS is 5% solar and 1SVK18, I think, is 3% solar, more or less. This galaxy has also been observed with James Webb now, and has also optical observation. In particular, the data we have been using are from the Cycle 2 JWST program from Aloisi and Hunt, Alexandra Aloisi and Leslie Hunt. We have been working on the comparison between the James Webb data and the KCWI data in the optical that can reveal the very high ionization helium-2 emission that is comparable in terms of ionization potential to the oxygen-4 emission that we revealed in the mid-infrared. And also this galaxy, interestingly, shows an extended neon 5 that was not known before, which makes all this discussion even more interesting, because it's what is going on here. There are many works that are submitted now and also in preparation. But just to show you a bit of it, here there is the one plot that is from the presentation paper that shows the neon 5, neon 2 versus the neon 3, neon 2 line ratios. All the points that you can see here on the left show the typical star forming and AGN galaxies in the local universe, while the 4 stars that you see here instead are extracted regions from the map that you can see here, are four extracted apertures from the northwest part of 1SVK18, and they are all located. They have all neon 5, neon 2 line ratios that are also compatible with the AGN-like emission, let's say, and not the star formation. Just to show you the comparison with the case of SBS that I was showing just a few moments ago, SBS, like more or less, is located in this region over here. So it has line ratios that are a bit higher than 1SVK18, but still we are talking about comparable values, which is really interesting, and definitely there are things that we need to learn about this. But there is much more that we can do apart from studying the ionization source with these MIRI MRS data. In particular, well, this plot is a very complicated plot. This is from BER 2021, but it just shows the ionization potential as a function, well, for the different elements that you can see. And here I highlighted with the circles the high ionization transitions that are only available from the mid-infrared and not from the optical. In particular, the oxygen 4. Here I want to focus on the oxygen 4. And the work that our postdoc Ryan Riccarboth is doing is putting together the information from the mid-infrared using the oxygen, for example, the oxygen 4, and the information from the KCWI data, where you can study the oxygen abundance from oxygen 2 and oxygen 3 emission lines, in order to create a new map of the gas phase metallicity in 1SVK18 that takes into account of all it takes into account also the oxygen for the calculation. Sorry. the point of this work is to show that nearby high redshift analogs that have these very high ionization emission lines that are not typical of all star-forming regions. It's like the point is that it's important to take into account that including also the oxygen 4 is essential to correct the gas phase metallicity in this system. These are very, like, I won't want to spend much about this. This work is resubmitted and hopefully will be soon on archive. What Ryan has been doing is testing the measurement of the metallicity using the, so what he did was, that is shown in this plot, is that he studied the metallicity by calculating the oxygen abundance only using the information from the oxygen 2 and the oxygen 3 and the direct method. And he took into account, and then he measured the metallicity also considering the oxygen 4. So the measurements also considering the oxygen 4 are shown on the y-axis in this plot, and the measurement without considering the oxygen 4 are shown on the x-axis. On the, and in particular, I want to focus here on the right side. In this case, the difference between the y and the x measurements is even bigger, because the median is going is very the median that is shown in blue is very different from the one-to-one relation, and the reason is that for the calculation of the metallicity on the x-axis is not taking into account the is just taking into account the low ionization density in the direct math calculation of the oxygen abundance. So it's just taking into account the oxygen 2 density instead of taking into account that when you measure the oxygen, when you measure the ionic abundance of the oxygen 3, you need to take into account the higher ionization density tracer, for example, the argon 4 in the optical. So taking into account the oxygen 4 and taking into account the corresponding high density tracers is important to have a good measurement of the gas phase metallicity in systems similar to 1SVK18. In the work, there are even more details that I don't want to discuss right now, but stay tuned because it's really, really interesting. Finally, and I am a bit long, so I will try to be quick. There is the MIRI MRS data are not only giving us an overview of the ionized gas, but they also allow us to trace the warm molecular gas, because we can also see H2 rotational lines in the mid-infrared spectrum. So the main idea behind my cycle 2 proposal was to explore these H2 transitions in the mid-infrared to calculate the molecular gas mass in these local analogs. The reason why this is interesting is because in metal poor systems, it can be very difficult to measure the molecular gas using standard tracers, for example, the CO, because in metal poor conditions, there is, of course, it's more metal poor, and so you have in general less carbon, plus less carbon and oxygen, and plus you have harder ionization radiation from stars that can dissociate CO much more easily than in normal star-forming galaxies. This is a very beautiful scheme from Madden 2020. So the point was to try to study the H2, to study the molecular gas directly tracing the H2 rotational transitions in the mid-infrared in order to reveal the molecular gas reservoirs for these lower redshift analogs. And this putting together the works from my proposal and the proposal from Aloysi and Hunt on 1SVK18. Plus the information that we can get from the CO using IRAM and ALMA, and we get this, yes, and we have this information from literature plus new observations that we got in the last couple of years. This project is still this project is still in preparation. There is now more information coming from the literature. For example, here there is a work submitted for the Galaxy 1SVK18, where Leslie Hunt studied she studied the H2, the different rotational emission lines of the H2. She studied the distribution of sorry, I will find the words. She extracted different spectra from 1SVK18 and studied the different H2. My God, I don't remember the word. Anyway, the excitation diagrams, sorry, of the H2 in order to define the temperature of the gas and also the content of warm molecular gas for this galaxy. Plus, there is now a recent work from Telford 2025 for the low metal poor object LEOP. This is also a very metal poor system in the local universe, 3% solar. And they published, I think, the first detection of H2 in this kind of environments. So this is the kind of context where we want to explore more. And there is the work in progress from Macarena Garcia del Valle. She's looking at the H2 distribution of the different H2 lines, plus which transitions we can study in order to measure in order to get an estimate of the warm molecular gas mass in these systems. These are preliminary results for the galaxy SBS, but she's working on the 6 galaxies of our data. And so stay tuned for more information about the warm molecular gas contents of these systems. And finally, last thing, of course, in the mid-infrared, we can also get information about the dust. Usually, there are many pH features that we can see in more metal-rich environments. At the metallicity of these objects, it's difficult to see pH. pH, I think, well, in general, it's difficult to observe them at metallicity that are below 20% solar. And we think that we got the first pH detection in one of the galaxy at the metallicity that is 15% solar. We are working on this, and this is the paper is about to be submitted. There is a tiny, here you can see, so this is the integrated spectrum that Macarena fitted with using Buffett. Sorry, 1 second. Using Buffett. And this that is zoomed over here is the tentative detection of the pH at around 11.3 micron. That is located more or less in this system, in this region, where we also see very strong neon 3, but also neon 5. So it's still, we are still investigating the conditions that we need to have this kind of emission, but this is really, really interesting and promising for future works. And I want to conclude over here with with the conclusions of all of our works in progress. And I think that I will go directly to my conclusions. Thank you very much for your attention.
Thank you very much, Matilde, for this impressive work. Congratulations.
Yes.
And now take some questions.
Thank you very much, Martina, for the very beautiful talk. Yeah, so I have a question and then a comment. My question is that have you considered the possibility of chemically homogeneous stars to contribute to the hard ionizing photons that you need to reproduce the observations of SBS?
Sorry, can you repeat the question?
Have you considered the possibility of the chemically homogeneous stars to contribute to the production of the hard ionizing photons that you need to explain the properties of the SBS? I'm asking because these stars are the outcome of the evolution of massive stars, rotating massive stars at metallicities similar to those of SBS and Brunswick 18. So then these stars could be a possible contributor to the to explain the high ionizing spectra features that you see.
I have to sit down. So yeah, this is it's still we still need to go into the details. Actually, I would like to explore more the chemically homogeneous distribution of SBS using news data, for example, because we can really map the so this is not something that we are looking for. What we are looking at is more the combination of X-ray binaries and the intermediate massive black hole models to see if there is a way to reproduce this kind of ionization transitions. But I would love to talk more about this.
Yes, because we just published a paper where we discuss the models for such stars. And they can, for example, there is a combination of such stars that can reproduce the helium-2 ionization budget in Brunswick 18. And since these two galaxies have the same similar metallicity, so this could be also a possibility to contribute to the high ionization in SBS. I think it's interesting for you, for your work.
Yeah, I would love to talk more about this.
Yes, of course, as you want. And the comment that I have is that well, we just published a letter in Astrophysical Journal that is already accepted and available in the archive, where we report here. This paper is here from our group. We report the detection of the neon 5 from James Webb in Brunswick 18, and we published the map, and also we studied the spatial correlation between the neon 5 and the helium-2 in Brunswick 18. I don't know if you're aware of the paper, but it's already published and in the archive. Thank you.
Very much. Yeah.
Yeah,
no.
You can sit here.
No, I'm okay. I can sit here, yes.
Yeah.
Thanks so much for your talk. You said that you have news data for SBS, right?
There are available news data on the archive.
Okay, so I guess that you can have a look on how the different eventual kinematical components may have an impact in measuring the fluxes of the emission lines to then estimate the land ratios. So my question is, are you aware of any different kinematical components in such an object?
So the point is that news spectral resolution is good, but it's not high enough. So what you see, if you look at the news data of SBS, you will see that there is a broad H alpha coming from some of the regions. I think that the broad H alpha is kind of extended and is coming from well, basically it's coming from the kiloparsec region where there is star parse going on. And so the problem of news data is that there is not enough spectral resolution and spatial resolution. The broad H alpha can be fitted with like 5 Gaussian components, so needs a lot of kinematical components. And while the other emission lines can be a bit more narrow, so it's not easy to complement like to do a really comparison of the different kinematical components. And so we would need higher spatial resolution and spectral resolution data to understand what's going on. There is a work published by Isotov 2006 that use giraffe, either Argos and giraffe. It's like it was I don't know if it's still available, but in that work they showed a very high spectral resolution, and they were looking at the region where there is the starburst, and they could reveal multiple H-alpha components, and they interpreted that as a super bubble that is expanding. But they didn't see any sign of a very broad H-alpha going on. And I don't know if that is because with the very high spectral resolution, they were missing this very broad component. Maybe there was not enough signal to noise to get the information on the broad component. Or if it's that in news we see a very broad component because it's a composition of all these very narrow components inside this.
Yeah, but even if you don't have any broad component, you may have for the very same line, emission line, say oxygen 3, for instance, you may have different chemical components that if you measure as a single line, you're measuring the flux in a wrong way, and this have a direct impact in what you're considering then as a line ratio when you use that line. So what was my question? If you take into account that maybe when you measure the fluxes for calculating the line ratios, your different components that may have different fluxes.
Yeah, for the infrared, for me and us, we don't see any sign of multiple components. So we are really comparing the narrow components one, yeah.
Thank you. That's an impressive work. Congrats, Matilda, seeing a lot of data. I have many questions, but let me focus on the ultraviolet with the glassy, because I don't know if I understood correctly. You mentioned that the difference between the density that you get from the sulfur 2 lines in relation to carbon 3 is 2 decks. You said 2 decks. This means that if sulfur 2 is around 100, you have more than 10 to the 4.
Yes.
That's a lot.
Yes.
That's impressive.
Yes, it is. It's the typical, that is the median. Then in different systems it can be a bit different, but the median value is really 10 to the 4 for the carbon 3 and 10 to the 2 for this.
And this has implications for the chemical abundance. You later mentioned for 115 that you do get the density for argon 4 for oxygen 2 plus, but I didn't get how much this affects the final determination of oxygen. In 118, this can be important because if we assume that it was around 5% of solar abundance, this enhances how much the abundance of 118, taking into account this.
So I think that I don't remember now the carbon. I don't remember now the values exactly for 118 for the oxygen 2 and the carbon 3 densities, but I can let you know later. They are written in Ryan's paper. It takes into account that the difference that Ryan finds when taking into account the density is that in general the gas phase metallicity is 1 dex higher around well, if you take into account the high density, instead of getting 7.1 for the oxygen abundance, you get 7. So when you go to very low metallicity, you can have differences up to 0.1 dex. And this is instead the effect becomes negligible when you go to higher metallicity values, so around 7.4. We are still talking about the metallicity of 118, so we are in a range of very low metallicities.
Affects much less that not taking into account the oxygen for contribution, the underestimation of the ICF in 118.
Yes.
Okay.
Yes, it seems that the density is even more important than considering the oxygen 4.
That's amazing.
Yeah.
Thank you.
And the impact of the density is important even when measuring the nitrogen abundance and also other quantities. And these are all things that we are looking at in classy. So the density seems really a very important factor to take into account.
Very much for the very interesting talk. I had a question about the SBS. So that system showed a high FE over O ratio, no?
Sorry.
The SBS,
Yes.
that system showed a high FE over O ratio abundance.
Mm,
Or no, or maybe I'm wrong. But anyway, did you try to see the abundance of neon over oxygen or something like that to get like to see from the nucleosynthesis point of view if we can understand something from that point?
Yeah. Yeah, no, we have not calculated the neon abundance from the mid-infrared data. This is something that is in the plan. Like one of our collaborators is Carla Arellano Cordova. She's the expert of metallicity and metal abundances in our group, and she has explored the neon abundance using the optical side. So she used the neon lines in the optical. And she did that not specifically for SBS, but she looked at the classes survey. And for the neon abundance, she didn't find any variation, any significant variation with respect to oxygen, as you would expect. And she is now instead working on the nitrogen abundance. And for nitrogen, she finds interesting results. And I think that the paper should be out on archive in these days. But yeah, for the neon, using the mid-infrared, this is work in progress. Thank you.
We had to have many
Sure,
questions. So Matilde is here for 3 days along the weeks. She is leaving Friday, so we have time for someone want to ask her or comment something with Matilde, so she will be around in the evening. Thank you again. Thank you very much for listening.
Thank you very much.